page. So let me say that my calculus class has been complaining that I don't know where I'm going. So before you complain, the agenda for the next few classes would be maybe generating functions. And then we will do plus minus epsilon here. So we will follow this book for a while, generating functionality by Will. Since we already, we reached that Catalan number. So the idea is, so overall, my goal was that overall plan was that about half the course would be a survey, and the other half would be a deep dive, a deeper dive, let's say, into a specific topic. And the topic which I want to go in is partitions, and plus there is some associated number theory. So the first half of the course would be until the midterm break, and that's still quite far away. So we'll go through Wilf's book, and then some aspects of Wilf's book are basically to do with partitions. Uh, those we want. So the plan would be that so Wilf actually covers a lot of ground. So a lot of combinatorial stuff he does, and um, what we do is by going through it, we examine many combinatorial objects. So we examine some combinatorial. But then there are some things which he doesn't bother about. So which you see out, in the papers and so on. So everybody should know at least what they mean and so on. So we will examine them. So this part of the course is, I would say, wide and not deep. And this is a much deeper thing into one thing. So we go into one area and try to find problems. So these are more or less easy if you understand them, but there are a large number of them, and these are also easy, but you study things in more detail and you get more types of results there. And this is very classical, Euler, Jacobi type of stuff. Plus recent interest is there. And one particular highlight I want to do is actually prove if we can prove one of Ramanujan's results. If we can. Anyway, so meanwhile, so this is the plan, such as it is. And today I want to just first begin with just do a little bit, redo a bit of paths. I think we sort of rushed through this. So let me just explain this. And we rushed through for good reason, because I didn't know how to do that. It looked very easy when I wrote it in my notes, but it seemed a little bit more complicated when I came to class. So anyway, so we recall that paths from 00 to NN, which do not cross y equal to x. This is Cn. So let's do by example. So we are bothered about 3, 3, n equal to 3. and one of them is with this guy, 1, 2, 3 this way, 1, 2, 3 this way. Then you can do 1, 2, that's another one. Then you can do 1, 2, then this way, and this. Then you can go 1 up, 1 down, 2, and then you can do mm, so in all these, the line y equal to x is this guy. Fine. So I want to isolate, figure out this chap, and the point is that you take the, if you take the um, first place going from bottom to top where it crosses the y-axis, crosses this guy. So the first place where it touches this line, these two guys, this guy touches here, and these two touch here. So take the first chap where it touches, and then when you look at it, so here it touches at 3, 3, right? So this corresponds to when it touches the first place where it touches here. Suppose it touches at k, then this corresponds to the paths which are on from this point to this point. So the first guy touches here, it corresponds to these paths. So basically going from 0, 0 to 2. So if this is the point where it touches, then this corresponds to, these two correspond to C2 and C0. C0 being there's no path, and C2 being the paths over here. So this is touching at k equal to 3. K equal to 3. This one is touching at k equal to 2. This corresponds to this path, which is C1. So k1 less than this, and then this is C1 again. Number of paths here. And these guys touch k equal to 1. So C0. So there's only one path here, and then there are two paths over here times C2. So I mean, by this example, so we cut the path at the place where it first touches y equal to x. Okay, so this is the idea. Something, suppose this is the first place it touches, and it's over here. Then this part, if this is the kth part, then this part is, it has ck minus 1 paths, because all these paths do not, they lie above this part, they lie above this, and these guys are cn minus k, and this should give you cn. So let me erase this. So cn is equal to ck minus 1, cn minus k, k going from 1 to, and then what you do is you replace n by n plus 1. And you get Cn plus 1 is equal to k going from 1 to n plus 1, Ck minus 1, Cn plus 1 minus k. And then you shift this index because k is going from 1, so this is, you can do k equal to 0 to n and Ck. And here it is replace k by k minus 1. And you get n max. So you're replacing k by k plus 1 here in shifting. Shift the index, replace k by k plus 1. And here you're pushing it, here you're just replacing n by n plus 1. Okay, so this should prove the recurrence relation. Is that fine? Is that okay?
Yes, Professor.
Yep.
Okay, so yeah, I rushed through that, and the reason is that I was confused. So, but anyway, I think I will give you homeworks on this problem so that you won't be confused when you teach this to somebody else. Okay, so next I want to just verify before going on to some simpler example. Um, um, verify the, I quite like this green pen. Let's try this one. Verify the formula. Oh, that's nice. For Catalan numbers from its generating function. And the reason I'm doing that is because this is a common thing. I mean, one has to do a lot of this kind of calculation in this business. So I don't know how much I can give you practice on these, but these were, I mean, in our time they were done in calculus a lot, but now these are sort of old-fashioned. Let me see if I can give you some exercises to help you practice. This is manipulations, so manipulatorics. So let's look at this Cx, which is Cn x to the n. I hope I am recording this right. Yeah, it seems like. So Shivam, I must say that you have done your job brilliantly because because in the calculus class we forgot to record and we realized only towards the end. So now there will be like some complaints. So you can go back to sleep if you wish. Now that you've done your job. Okay, so this is 1 minus, this is what we calculated last time. And I want to derive the formula for Catalan numbers from this expression. So we recall that 1 minus x raised to minus a was summation k going from 0 to infinity a sub k over k factorial x to the k. So c of x is 1 over 4x 1 minus, and this is 1 minus 4x raised to the power 1 half. So if you just plug it in, this is minus 1 by 2k, k factorial, 4x raised to the power. So this is, the first term is 1. The first term is 1. The second term is minus 1 by 2, 1 over 1 factorial 4x raised to 1, and so on. So 1 minus 1 cancels basically, and you get minus sign summation k going from 1 onwards. And 4x raised to. And this is
Professor, shouldn't the denominator be 2x, 1 by 2x?
denominator should be
2x, right? 1 minus root 1 minus 4x by 2x, I think.
this 4x. Which denominator are you talking?
Yeah, that one. That one.
This is 4x, right? So I'm keeping this outside. This guy is over here.
No, I'm saying I think it's 2x from the quadratic formula.
Which 2x?
Instead of 4x, I think it should be 2x.
Oh, it's 2x, is it?
Yeah.
Yes,
Okay, it's
Professor.
easy to recall because I've written it somewhere before. Oh, there you go. Okay, all right. Got it. So some delicate editing. Uh, this is what you want, right? Now it's okay.
Yep.
Okay, so this is 1 over 2x, and there's a minus. So there's a minus 1 by 2 um, k, and so what I do is I take out this minus. So what is this minus 1 by 2? This is minus 1 by 2, 1 by 2, 3 by 2, and so on. And this is overall k terms. So what I do is I remove the 1 by 2. So there's already a minus sign. There's already a minus sign, and then I take out a minus 1 by 2 from here, and then I have a k equal to 1 to n, and then I have a 1 by 2 is for k minus 1, k factorial, 4x raised to, and in fact I can take out this guy also. Is this clear? So there are k terms. I mean, minus 1 by 2 sub k is minus 1 by 2 minus 1 by 2 plus 1, so on up till minus 1 by 2 plus k minus 1. So if I take the first term out, I get this and I get this out. And then this k also I can, so I get a 4 indeed again. And this minus sign cancels. And there is a 4x2 which comes out. And I have k going from 1 to n, 1 by 2, k minus 1, k factorial, and 4x is for k minus 1. So now this cancels. And I get this. And here I do k going from 0 to, and by the n, it should be infinity. Sorry about that. What is n? There's no n there. So now I'm shifting the index and I've got 1 by 2 sub k. And now this becomes k plus 1 factorial. So I take out a k plus 1 and k factorial. And I have 4x raised to k. So earlier it was starting from k equal to 1. So the first term was when you have k equal to 1, 0 here, 1 here, and 4x raised to 0 here. And now also you have the same thing. So we just shifted the index. So this is shifting the index. Okay. Uh, so this is let me play around with this 1 by 2 sub k now. So it's 1 by 2, 1 by 2 plus 1, so on until 1 by 2 plus k minus 1. So this is 1 into 3 and so on up till 2k minus 2, 2k minus 1. And there are, why is it coming out? So I can understand. There is a mystery. Okay, and there is a 2 raised per k here. And what I do is I multiply by 2, then 4, and so on. 2k minus 1 into 2k. Also multiply by 2 into 4, and so on. So on top I get 2k factorial. At the bottom I get this 2 raised per k and then another 2 raised per k, and then I get 1, 2, 3 up to k factorial. Is that okay?
Yes, Professor.
Okay, so we're back here. This top part is basically um, let's assume that this was in a rough part of the thing, and the same equal to sign works. So k going from 0 to infinity. Um, I have this animal here. Then I have a k factorial here. I have a 1 over 4 raised per k here. And then this k plus 1 is already there. And another k factorial. And I have 4x to the k. And now the 4 disappears. And I get, so 2k factorial, so I get the 1 over k plus 1. I get the 2k over k. And I have x to the k. And recall what were we doing? We were doing ck x to the k. So this implies that Cn of k is 1 over n plus 1 as required. So yeah, this is the end of this calculation. Um, so there are, just to summarize, we yeah, this, there was this way, which was short and beautiful. It made pictures, and then there was this way, recurrence relation, which was also short and beautiful, but it took time for me to understand it and explain it to you. And then from the recurrence relation, you get a generating function, and from the generating function, one can get the answer. But I mean, this is anything but beautiful. I mean, some people, including me, I'll be like this kind of calculation. It's a it's a interesting game. So, any queries? Any queries on this calculation? Then everything okay? Is that fine?
Yes,
Okay.
Professor.
Yeah. You said something, Peter?
No, no, I suggest yes, like it's fine.
You said yes unilaterally for everybody. People haven't even woken up to answer my question, and you're saying yes for them.
I had a small question.
Yes.
How do we get from the minus 1 by 2 sub k to plus 1 by 2 sub k?
Yeah, you get. Yeah, actually, you don't get there. You get somewhere else. So let me do it here. So this is basically minus 1 by 2, minus 1 by 2 plus 1, which is plus 1 by 2, 3 by 2, and so on.
Okay,
K.
okay. Right,
These are
right.
k terms. So this is minus 1 by 2 times k minus 1 terms.
Okay, yeah. Makes sense.
And we can only do that because k is bigger than equal to 1. So we already deleted the first one. Okay, so this is like a little more complicated, um, you know, thing of generating functionality. It comes somewhere ahead in Wilf's book. But so now what we'll do is a simpler example. So, I mean, this might be boring for you because you've seen it so many times, but I mean, everybody, at least in undergrad, should see once in their life. So I include this example even in the calculus class. Let's just go through it. It's a classical example, and it's surprisingly, uh, deep in the sense that this idea, whatever you get over here, is applicable a huge number of places. And I don't know. So here's the Fibonacci sequence. So you define f0 as 1, f1 as 1, and fn plus 2 as fn plus 1 plus fn. And this is for n bigger than equal to 0. We've already, I showed it to you last time. I think the first few Fibonacci numbers are 0, 1, 1, 2, 3, 5, 8. What comes next? Somebody tell me.
13,
Then,
21,
so
34.
you add the sum of the previous value. By the way, I hope somebody has told you what the three dots mean. What do you mean by this? I mean, I hate it when people put four dots. I mean, they put four dots if you put a period here. That's the fourth dot. This is an ellipsis, and it means and so on. So don't put dot, 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 dot in your homework. I will cut 5 points. Okay. So what we want to do is find a formula for Fm using generating functions and other ways to get you an idea. And before I go on, let me suggest that there is a journal called Fibonacci Quarterly. This is a journal which is dedicated to Fibonacci numbers and their properties. And even today, very, very common student project is to find some new Fibonacci results and put them. So, you
Professor,
know, yes.
Fibonacci starts from 0 or 1? We have taken 0 also.
Yeah, if you start from
It
here, it
starts
starts
from
from
0.
1. If you start from here, it starts from 0.
Okay.
Um, yeah, actually, you're right. This should be 0. Usually, this is 0. So I wrote 0, 1, but over here, But there are some numbers which sometimes they start from this place and so on. 0 and 1 is fine. Um, if you're working in orthogonal polynomials, then you go 1, 1, so it's a little confusing. So, uh, anyway, doesn't matter. So, okay, so we have so method 1 is we solve a linear difference equation. Okay, so this is the difference equation. And it's very similar to how one does it in differential equations. We assume that the solution is of the form alpha raised to n, or I'm using R because Wilf uses R. Okay, then R raised to n plus 2 is equal to R raised to n plus 1 plus R raised to n. Now I've written something wrong here. And this means that R raised to n, R square minus R minus 1 is equal to 0. So there is a solution. This is a solution if R square minus R minus 1 is 0. So R is minus B plus minus B square minus 4AC divided by 2. So we have a notation that R plus B 1 plus square root 5 over 2 and R minus B 1 minus square root. So these are solutions of this equation in general, particular solutions of this guy. And we claim that all solutions are linear combinations sorry, of R plus and R minus. So the general solution is of this form.
Are these also called, Professor, golden numbers or golden ratio?
Yeah. Something. One of them is called that. So, this is the general solution, and from here one can calculate that if f0 equal to 0, this means that a plus b is 0, and f1 is equal to 1, this means that a r plus b r minus is equal to 1. And from the first equation, we have a of r plus minus r minus is equal to 1. So a is equal to 1 over r plus minus r. And b is, so what is this? I mean, r plus is 1 plus square root 5 over 2 minus 1 minus square root 5 over 2. You get, uh, square root 5. And b is minus a, which is minus 1 over square root. So the solution is Fibonacci numbers are 1 over square root 5 r plus minus r minus. So this term, just look at it. So 5 is, square root 5 is 2 point something, right? 2.2 something. 1 minus square root 5 would be minus 0.2 something. No, minus 1.2 something and divide by 2. This is something smaller than 1. So as n goes to infinity, this guy goes to 0. So in general, Fn is approximately equal to. In fact, you can prove Fn is 1 over square root 5, the something like this. The latest integer function, the floor. So this is the dominant term. It's an exponential function, and there is a this term goes to 0. So we've got one solution. This is the solution. You know what? I'm going to use the highlight. Much better than drawing a box, which I can't draw. Okay, any questions on this method? So it's a difference equation, very much like a differential equation, and one solves a difference equation. And there are techniques for solving difference equations which are exactly the very analogous to differential equation. That you try something and then when you get it, you prove that's the right thing. So, I mean, there is a what one says is that this guy, whatever this a times r plus n plus b times r plus n is sort of a general solution, and then every solution has to be a linear combination of these because these two guys are linearly independent, so you have to prove all those things and then get whatever you. So similar to the theory of differential equations, there is you can find the theory of difference equation. Okay, so here's method 2. And here we use generating functions. So again we have fn plus 2 is equal to fn plus 1 plus fn, and f0 equal to 0, f1 equal to 1. So let's start and let f of x be fn x raised power n and going from 0 to 3. And this is called the ordinary generating function of fn. So this term ordinary, uh, so we'll know what is not ordinary at some point. Okay, and the technique is simply multiply what we did earlier, multiply both sides of star by x to the n plus 2 and sum over n going over 0. And we get, so on this side we get summation fn plus 2 x to the n plus 2, n going from 0 to infinity, and here we get x fn plus 1 x raised to n plus 1, and going from 0 to infinity, and here we get x square summation fn. Okay, this is what we needed. So this part is easy. This is fn x square of fx. This one starts from n equal to 0. We are starting always. So this one starts from f1. So the first term is f1. So we have to remove. We have basically f of x minus the first term, and that happens to be f0 times x raised to 0. And here we have to remove two terms. So it's f of x minus f0 times x raised to 0 minus f1. And this is where the first two terms come out. Okay. So we get f of x, and this is f0 is 0, luckily. So that's one good reason for putting f0 equal to 0 rather than 1. I mean, you get the same solution, but you start with 0. And f1 is 1. And this is x fx plus x square fx. And this will give you f of x 1 minus x square is equal to x. So fx equal to x over 1 minus x minus. How do you do this? We just use formula. Okay. Now note that 1 minus x square is 1 minus r plus x times 1 minus r minus x. So if you recall, r plus was 1 plus square root 5 over 2. R minus was 1 minus square root 5 over 2. So r plus times r minus is equal to, you multiply the two together. So it's 1 minus 4 over 4, which is equal to 1 minus 5, which is equal to minus 1, which matches r plus r minus will be 1. So minus this guy matches. So all these things match. Yeah. So so f of x is x over 1 minus r plus x times 1 minus r minus x. And what we do is we write it in terms of partial fractions. So we write it as a over 1 minus r plus x plus b over 1 minus r plus x. So do you remember partial fractions? You probably do, but it's not so clear I remember it. But anyway, this is what we do. So we multiply the two and compare the numerators. So we have x is equal to a 1 minus r minus x plus b 1 minus r plus x. This is an identity. So I can choose any value of x that I want. So I choose x equal to 1 over r minus. By doing so, I get rid of this term. So this implies that b r minus r plus is equal to this side I've put 1 over r minus and then it gets cancelled. So it's actually 1. So b is equal to 1 over r minus minus r plus. And we choose x equal to 1 over r plus. So this term goes away. So on this side you have 1 over r plus is equal to a r plus minus r minus divided by r plus. This means that a is equal to 1 over r plus minus r. So ultimately what you get is you get f of x is equal to a, which is 1 over r plus minus r minus 1 over 1 minus r plus x minus 1 over 1 minus. Okay? Is that fine? All right so far? And I think we had calculated r plus, no, we hadn't. So r plus minus r minus is 1 plus square root 5 over 2 minus 1 minus square root 5. So square root 5. So we get 1 over square root 5. Now this chap I expand using the geometric series. So I have k going from 0 to infinity. I have a plus raised per k, x raised per k, minus, and this one also I expand. This is r plus. So what did I use? I used the geometry. So either formally or maximum value of x is less. And we've got the formula. So what have we got? We've got f of x is equal to f of x, which was summation fn x raised per n, or fk x raised per k, since we're using k here. K going from 0 to infinity. So this implies that fk is equal to 1 over square root 5 r plus raised per k minus r minus raised per k. The same as before. Okay, so note, is that okay so far? Okay, how long have we got to go? Okay, 6. It's okay, so we have half an hour. Let's go. Okay, any questions so far? Is this familiar stuff? Have you seen it before?
I mean, it isn't discrete math, but I think all of us may not have done it.
Okay, wasn't discrete. Okay, that's good. Okay, so I'll draw some lessons, but first let me note something that what you can do is you can divide by fn plus 1, and you can write it as like this. So let's take phi of n to be equal to fn plus 1 over fn, and n going from 1 to whatever. So what this is telling you is that phi of n plus 1 is equal to 1 plus 1 over phi of n, which is 1 plus 1 over 1 plus 1 pn minus 1, so on, and you have 1 plus 1. So this animal is called a continued fraction. Okay, and in general, three-term recurrence relations of this kind are related to continued fractions, and they are related to orthogonal. So if they're the right type, then they're related to orthogonal polynomials, i.e. some kind of Fourier analysis. Very applied in many areas. So rather remarkably, this simple example, if you just mess around with a little bit, add a few x's and so on, they're related to lots of things. The three-term recurrence relations define orthogonal polynomials. By orthogonal polynomials, I mean exactly what you see in Fourier analysis. Uh, some integral is equal to 0 or 1, and then using that you can write any function in terms of that these functions, and then when you can do that, then the properties of these specific functions come into play. So this is actually very deep, and it is related to, it comes up in combinatorics. So orthogonal polynomials are very very related to combinatorial structures. So this is a central area, and continued fractions keep getting found in combinatorial contexts even now. So maybe we'll have an example. And one more thing, I mean, I would suggest if you look at Hardy and Wright, of course there are newer books. Um, so if you just chop off the polynomial, okay, this is going to be the ratio of this, but it's a classic example of an alternating thing which goes like this. So odd terms decrease, even terms increase, and difference becomes 0. So this is a theorem in classical analysis, in real analysis, that such sequences converge. And you wonder where they came from. They came from this kind of example. They came from continued fractions. This is a prototypical example of this kind of behavior of a series, where alternate terms go down, some terms go up, and their difference goes to 0. So I mean, the classical theorem in analysis in Rudin, for example, would be to show that this kind of series sequence converges. And the prototypical example is these continued fractions. And finally, let me make a comment that what did Ramanujan do? And many others, especially Shore, they looked at a sequence xn plus 2 equal to something like this. It could be qn plus 1 here from alpha. They looked at this thing, and now let's say x0 is equal to 1 and x1 is equal to something, x0 equal to 0, something like this, and now you get a polynomial in Q. Okay, and this kind of thing, Q Fibonacci number, uh, came up first in Schur's work in um, representation theory. So, you know what is representation theory? You know what
Is it the one where we
Huh?
represent Is it the one where you represent groups by vector spaces and do operations in one?
Yeah, yeah. Good. I was going to say I don't either. So, but you anyway, you explained now. So representation theory is, I mean, basically, they say all of mathematics is about about taking something and converting it into linear algebra. So this is a truism, you know. If you know, I mean, any function in calculus, basically, if you just go very close by, if it's differentiable and so on, then it looks like a straight line. So pretty much locally, it is a straight line, and the object of almost anything else is to look convert it into something linear, some straight line, and the word linear is associated with linear algebra, which is matrix. So everything is you try to look at it as a linear approximation first. If you look at it closely, it will look like a line. That's a fundamental thing which Newton did. Basically, he looked at. So ever since, all that we have been doing is basically trying to convert everything into a straight line. So if you look at most of computer science algorithms, they are searching for ways to use matrices and linear algebra to be able to calculate various things. So remarkably huge amount of stuff can be done in linear time or nearly linear time. And nearly linear means you could have some kind of randomization and get it. And the whole point is make it linear when we understand something. A straight line we understand very well, even though we can't draw it. I mean, I can't draw it for sure. But yeah, well, this looks straight to me. So, so that's the point. So it came up in Schur's work. It is the Fibonacci example is remarkably deep. Okay. So, anyways, let me briefly give you the combinatorics. So, stick to this guy. Fibonacci. So this is there's a nice reference for this. Uh, it's called proofs that really count, and this is written by Arthur Benjamin and Jennifer Quinn. So yeah, I mean it's available from wherever you can get to steal such books. So this guy Benjamin is very interesting chap. I haven't seen his talks, but he's a magician. He's also a professor. So every time, apparently, so I haven't met him, but every time he goes to some conferences and people basically want to go for lunches with him so that he can show them some magic tricks. And he quite obliges many times. So he's a professional magician. So, in fact, a lot of combinatorial people are, uh, are attracted towards magic and things like that. So they get into. There's a famous story. Um, he's a calculator. Yeah, maybe. So there's a famous story of this guy. Um, he ran away from home and he was doing magic tricks somewhere in New York, and then Martin Gardner saw him, and Martin Gardner used to frequent pubs where there were people who were doing magic tricks and so on. And there was this kid who was really sharp, and Martin Gardner used to talk to him. And then at some point, that guy said that he needs an education. He had run away from home, so Gardner wrote a recommendation to, I don't know, MIT or some big place. And basically, his recommendation was that this kid showed me the best, the two new tricks which I didn't know before, two new card tricks. And he got admission into graduate school. And there are all kinds of stories about this chap. He's a very famous mathematician. One of the stories is that he went to he reached late for a class, and the prof had written some problems on the board. So the statistics prof had written some problems on the board, and he copied them down as homework. And then he after a week he went to the prof and he said that he's done the homework, and it's the homework has been done, but he couldn't do all the problems. He's done 2 out of 4 or something like that. So the prof said, okay, just put it somewhere. And so there was this big pile. I mean, all profs, many profs, have a huge pile on their desk, and he put it on that pile. And then about a month later, the prof went hunting for him. Apparently, those were unsolved problems. And he was late, so he didn't know it was unsolved. So then he rapidly got a PhD after that. So he had solved some 2 major unsolved problems, which, first of all, he left it at the prof's thing. He didn't know they were unsolved. And secondly, the prof found it in that mountain at some point. So, if I'm late for grading, don't worry. Maybe I'll get back at some stage. But there is all kinds of interesting people who are in mathematics. I think it's Percy Diaconis, the story about. Okay, so let's look at combinatorial interpretation. So let Fn be so I'm taking small n, f, and the number of ways of tiling n squares with squares and dominoes. So what are squares? So what we do is we tile this guy, and we tile with either squares or we tile with dominoes, and dominoes are basically 2 cross 1. So you have a domino like this, and you have a square, and you want to calculate the number of ways of tiling a n square. So the total number of squares here is, let's say, n is 1, 2, 3, so on until n. This is a square. So we define f0 to be 1. Okay. If there's just one square, then there's only one way of tiling it. If there are 2 squares, then there are 2 ways of tiling it. One is with 2 squares, and one is with this thing, with a domino. And let's do 3 squares. So this is one way of doing it. This is one way, so I'm filling in, and this is one way. So f3 is 3, and by induction it follows that these are Fibonacci numbers, only shifted. So fn plus 2, I want to prove this. So this is the number of ways of tiling n plus 2 squares. And so there are 2 cases. One is that the last guy is a domino. If this is a domino, then this is the number of ways of tiling Fn. And if the last chap is just a square, Okay, then this is the number. F of n plus 1 is the number to tile the rest of them. So this is true, and f of 0 is equal to 1 and f of 1 equal to 1. So these are shifted Fibonacci numbers. So let's say f of minus 1 we define as f0. F0 is f1, f1 is f2, and so on. So fn is fn plus 1, small fn. Okay, so let me prove one result. So any questions on this?
Professor, so we were, what's the thing which we're covering? Like a n cross 2 square, n cross 2 cube, rectangle.
N cross 1. So n squares in a row. So 1 cross n.
Oh,
So it's a long strip. So it's a strip of 1 cross n strip. So 1 row and n squares.
so how do we place the trominos on this?
So either you place a square or you place a domino. So square I'm describing as an empty thing, and domino is is a 1 by 2 thing. So maybe I should have written 1 by 2.
Okay.
Right? So this is a domino looks like this, and a square just looks like this. I mean, they're both filled in, but usually, so this is a domino. So there are all kinds of problems with dominoes, tilings, and so on. You can tile them like this, so on. Like you can tile this. So here he's just taken this problem, and it's Fn. It turns out to be the number of ways of tiling an n square with squares and dominoes. The simplest kind of tiling problem. Is that okay? Does that answer your question?
Yeah, yes, Professor. Yeah.
Professor, how would we use induction here?
Sorry?
Oh, we can use double induction. Yeah, two values.
What?
Okay.
Where?
So for generalizing the general term, right? For like 1 cross n general, fn is fn plus 2 is fn plus 1 and fn. How do we generalize it, right? Prove it that this will hold through induction only, right?
This is. I mean, I just said that it's, first three terms are the same, so rest must be the same. But uh, i- this is the proof that fn plus 2 is, what are we doing? Fn plus 2 is, um, yeah, there are n plus 2 squares here. And so that is fn plus 2, and we split it into two parts. One of them has the last guy is a square, and the last guy is a domino. If it's a domino, then how many such are there? Well, that you can put any tiling in these n remaining squares. So that can be done in fn ways. And similarly, if it's a square, we know it's a square. The rest, to count the rest, we need to do n domino tiling. So that's n plus 1. So this whole length is n plus 2. So this much is n plus 1.
Yeah, got it. Thank you.
So I mean, you just break it into these two parts, and then together they account for everything in fn plus 2. So the theorem is that you sum up all these things. So these are very classic kind of millions of such identities are there, and I've also found a few. Well, you find all the time, and then you find somebody else has found them. So let's just try it. So f0 is 1 plus 2, for example, is equal to 3, and so n equal to 1. So it's f3 minus 1. Is it true? So F3 was 1, 1, 2, 3, and here we are taking n equal to 1. So 0, 1, wait, so this should be 1 plus 1, and it is indeed equal to 3 minus 1. It does work. So what are we doing? We take a, so proof, combinatorial proof for a n plus 2 board, right? So you consider a n plus 2 board, whatever, the n plus 2 elements, and you remove, uh, so consider all tilings of an n plus 2 board which has at least one domino. Okay, so there is one tiling which has no dominoes. It's the all squares one. All tilings which have no one domino, and this gives us, so this gives us the right hand side, small fn plus 2 minus 1. So this is RHS. Consider this, the number is uh, number of such tilings is, and now to get the LHS, what we do is, so you're taking all these tilings and they have some kind of a, um, uh, they have some um, at least one domino. So suppose the domino is here, the last two steps. How many such tilings are there? So we know that the domino is here, so the number of tilings would be Fn of them. Suppose the last domino is over here, then how many tilings would there be? Fn minus 1. Suppose the last domino is over here, then how many tilings are there? Fn minus 2, and so on. So this will give you F0. So consider the position of the last domino, and we get number of tilings with one domino equal to F0 plus F1 plus. Is that clear? Any queries? Any questions? Any questions? Is it okay? Okay, so do it directly. So well, let me just say that. So since Fn is equal to Fn plus 1, this implies that F1 plus F2 plus F3 plus so on up till Fn plus 1 is equal to Fn plus 3 minus 1, or replacing n by n minus 1, we get F1 plus f2 plus fn is equal to fn plus 2 minus 1. And in fact, since f0 is 0, it's equal to this. So this is also true. So it's the same identity actually, whatever we did. So adding an f0 in front and then shifting identities. So let me put a remark. Note that. So identities involving Fn are equivalent to identities involving F. Yeah. So essentially, the point of their book is everything, and then there is a claim. Uh, can be they're trivial actually, using one telescoping and two using the formula plus induction. Uh, Formula is basically the formula we wrote. This one, I think this is called Binet's formula. Not sure. And Fibonacci numbers have been this thing. So one exercise is try do this one like this, like these methods. Using these two methods. So you know what telescoping is, of course. Everybody knows how to telescoping. Okay, any questions? Okay, so I'm done now. Um, we will be following a little bit more of generating functionality. So this was the first example there, and Catalan numbers come somewhere over there. And the basic, so actually every course that I teach, I start with very good intentions. So I mentioned the minimum energy principle to somebody on the classroom. The intentions are always to do the minimum work possible and do it, but then I don't know what happens. Somehow I want to do something else. But here we will. I really like Will's book. I also learned a lot of stuff from Combinatorics in just very pleasantly from that book. So I want to follow it to some extent. But we can't. I mean, reading the whole thing might take the entire semester. So I don't want to do that. So we'll read it for a couple of weeks, then we'll read somewhere, and then we'll stop. But meanwhile, I think with those couple of weeks or maybe 2 3 weeks, will gather a lot of information about many combinatorial objects, some intuition. So, okay, work hard on your assignment. Um, Remember, I'm still suggesting that please do discuss with each other, um, but write your own solutions and try on your own first, and write your own. Programs are very distinctive. So your way of solving program would be the it's your way essentially. And each time you do something, you you will learn something on your own if you do it on your own. So later on, we will require more complicated programs. I mean, it helps to sort of generate these objects. So it does help to generate recursively sets or these, because when you're really doing research, then you need to learn how to generate it. Then only you get your understanding in it. So, but right now, use the Sage. Just get familiar with Sage and use Sage to generate things and to get done. Shivam, you can also try Sage.